Hello students, in this video I'll be talking about the topic called as decision tree. This comes under the subject analysis and design of algorithms and the subject code is BCS 401. This comes under topic 1 of module 5 for the ADA subject. The topic is decision tree. Suppose, imagine like this, you're planning to go to college today. You're planning to go to the college today and you're deciding what to wear. Okay. You're going to the college and you're deciding what to wear. Suppose it's a very hot day. It's a hot day. Okay. So, what are you planning? If it is hot, then you will plan like, okay, I will wear a simple cotton kurta and a leggings and I'll go to college. Okay. If it is not, then I would wear jeans and maybe a shirt. See here, there is a condition. Okay. There's a question. What should I wear? Based on there is a condition. Condition is whether it is a hot day. And when you answer that condition, it is going to lead you to two results. One is wear kurta and leggings. The other one is wear jeans and t-shirt. Okay. So decision tree is works something very similar to this. There will be a question. Based on the question, there will be a condition. And based on the condition, there will be some outcomes. Okay. So that is called as decision tree. Let me take one more example. Suppose I want to check whether a student has passed or failed. Student has passed or failed. So this is the question. Condition is, let's say if the mark is greater than 50. If the mark is greater than 50, then the outcome is, if it is yes, then the outcome is pass. Otherwise, the outcome is fail. Okay. So how can you define this? You can say that there is a question. There is a question, and when answered, it leads you to two different choices, and the choice leads you to the final result. Correct? So there is a choice. If the mark is greater than 50, the choice is yes. And based on that, we will get the result as pass. If it is not, you will get the result as fail or the student cannot go to the next grade. Okay. So this is decision tree. So let us look at the definition. See here, a decision tree is a conceptual and analytical tool often used in algorithm analysis, particularly in decision-based algorithms like comparison, sorts, searching, and game trees. While you're doing comparison, okay, based on the comparison, it would lead you to different types of result. So here a decision tree will come into picture. So you will have to remember this definition. Okay, this is not exactly like how in the textbook, but I have made a summary of it and you can write it like this. A decision tree is a conceptual and analytical tool often used in algorithm analysis, particularly in decision-based algorithms like comparison sort, searching, and game trees. There are few examples that they have given for decision trees. We will look at one of them at the beginning and then we'll look at the more complex ones. The first one is a decision tree to find the minimum of three numbers. Three numbers are given. You will have to find the minimum among the three. Okay. So let's take the numbers as A, B, and C. Okay, there are three numbers. I want to find the smallest among these three. First, what I will do is, I will compare the first two numbers, A and B. Okay, A less than B. Two outcomes will be there. One if it is yes, the other one if it is no. Okay, so here you see, if A is less than B, okay, if it is yes, that means A is smaller among A and B. Then again, in order to, confirm whether A is only the smallest, again we compare it with C. So A less than C. Okay. Again, this will have two results. One is yes, the other one is no. So A is less than B, yes. A is less than C is also yes. That means A is smaller among among B, A and C. That means I can clearly say that A is the smallest. Okay. Otherwise, if A is less than C, here you see if A is less than C, if it is a no, that means C is the smallest. Like this. Otherwise, if A is less than B, if it is not, that means B is the smallest. Okay. If this is no, that means B is the smallest. So what I will do is again check whether B is the smallest among B and C. Okay. If it is yes, if B is less than C, then B is the smallest. Else, C is the smallest. Okay. Let me explain this once again. Initially, I will take A and B. Okay. If A is less than B, that means A is the smallest, right? If it is so, then again I will compare A less than C. If A is less than B and A is less than C, then A is only the smallest. Else, if A is less than B, if it is yes, but if A is less than C, if it is not. Okay, that means here if there is a no, then C is the smallest. Again, you see here, A is less than B. If it is no, that means B is the smallest among A and B. Now you want to check whether B is smallest among B and C, so that you can know whether B is the smallest among the three elements. So if A is less than B, no. Then again we'll check whether B is less than C. If it is yes, then B is the smallest. Otherwise, C is the smallest. Okay, so this is how you will do the minimum of the three numbers. You will do the minimum of the three numbers. Next, we have the explanation regarding this. See here, there is an internal node. There is an internal node which represents a key comparison. So here there is an internal node which represents a key comparison. And the left subtree contains if the components is true. If this is true, the left component will be there. And if it is false, then the right component would be there. And each leaf represents a possible outcome for a given input. So each leaf represents the outcome. The number of leaves must be at least as large as the number of distinct possible outcomes. So here there will be three possible outcomes. Either A is the smallest, B is the smallest, and C is the smallest. So we have those outcomes. And the worst case number of comparisons equals to the height of the tree. Because you will do the comparison, right? That will become the height of the tree. The height will be total number of levels minus 1. Okay. So that is what. And we also have this formula for a binary tree with E leaves and height h. There are E leaves and height h. Then we have this, that is h is greater than or equal to absolute value of or a fixed value of log e to the base 2. Okay, this you have to remember. For a binary tree with e leaves and height h, the height will be greater than or equal to log e to the base 2. Okay, so that is what. Now, one more algorithm for selection sort. Selection sort. This is very important. In decision tree, usually they will ask this question to write the decision tree for selection sort. Algorithm you might have already learned, and comparison is also learned. So straight away I will go with the decision tree itself. Let me take three numbers A, B and C, and I want to do the sorting of these numbers. Let me arrange these numbers in the increasing order. I want to sort them. Okay, so I will sort them in increasing order. Let us start the steps now. So initially, see here, when you have this question, okay, for example, if I have the question like this, The outcome, I will write it over here before the condition is applied. For example, if it is yes, then what will happen, that I will write here. Remember this, okay? Then I will write the next condition. Okay. So let us go to the condition itself. So here, three elements are A, B, and C. So initially, I will assume that the order is A, B, and C. Now let me check if A is less than B. Okay, I will check whether A is less than B. If it is so, one result will be there. If it is not, some other result will be there. So if it is yes, I'll do the left part first and then go to the right part. So if A is less than B, okay, that means the elements will be in the same order. See here, the elements are in the order A, B, and C. Now, if A is less than B, means the order will be the same, A, B, and C. Now, again, I will check with respect to A and C. Okay, here I will check with respect to A and C. I want to make sure that A is in the correct order. So, I'll compare it with B, then I'll compare it with C. Okay, again, this will have two results. One if it is yes, and the other one if it is no. Okay, if it is yes, what will happen? See, if A is less than C, if A is less than C, that means this order will still remain the same because A is first, then B, then C. If A is less than C means the order remains the same, A, B, and C. Okay, let me erase all the unwanted things here. Okay. Next, what I will do is, I know that A is less than C. Then again, I will compare. A has come to its correct position, right? A is compared with B. A is compared with the C. So A has got its position. It's in the first place. But what about B and C? So B and C should either come in, B should come either in second position or in the third position. So in order to check for that condition, I will do this particular part, B less than C. If it is yes, and if it is no. Now you see here, A has got its position, okay. A has got its position. So A will anyways come at the beginning only. Now, if A is less than, sorry, if B is less than C, if B is less than C, that means the order is the same. A, then B, then C. But if it is not, if B is not less than C, if B is not less than C, that means C is the smallest. Correct? That means after A, there will be C followed by B. This will be the order. Okay. Now let us come to this part. See here. See, A is less than C. If it is no, A is not less than C. That means C is the smallest, right? B will be in its position only. But A is not lesser than C. That means C is the smallest. So this will be the order. Okay. So C has got its position. Now, just to make sure that B and A are in the correct position, I'll compare B and A. If B is less than A. If B is less than A, then this order only will be there. C, B, A. This order only will be there. If B is less than A. But if it is not, then the order will be C, then B, then A. This will be the order. Sorry, 1 minute. See here, if B is less than A, if it is not, that means A will come first, right? If it is not, like this. Okay, let us go to the other side. Now, A is less than B if it is no. Okay, I will keep A, B and C like this. I will check B and C whether they are in the correct position or not. Then only I will come to know. See here. So I will check B less than C. If it is yes and if it is no. Okay. Let us see here. See. So here, see, A is less than B. No, that means A is not at the correct position. Okay. See here, because of this, I will get first B, then A. Correct? Because of this condition, B is less than C. B is less than C means B is lesser than C. And then C will come here. So because of that, the result will be B, A and C. Now you see in the other side. Okay. A is not less than B. Okay. A is not less than B. No. So B is the smallest. Okay. Now you see here. B is less than C. B is less than C. No. If it is no, that means C is the biggest. A will obviously come here. Are you understanding? Let me explain this once again. See, A is less than B. It's a no. That means B and A is the order. But when it comes to this part, B is less than C. B is less than C. Okay, so C should be the smallest. Similarly for this one, A less than B. So again it will be B and A. But when you compare it with the C, okay, when you compare it with C, C is the smallest. See here. If it is yes, that means C is the smallest. B is the smallest. So this will be the order. So this is how it will be. Now what I will do is do the last comparison. I want to make sure that B and C are in the correct position. So I will check A less than C just to make sure. If it is no, then it will be B, then C, then A. Because B is in the correct position. If A is lesser than C, if it is not, that means C is the smallest. So C will come in the middle. If it is yes, then the order will be B, A, then C. Next, C has got its position. C has got its position. Now let us confirm whether B and A are in the correct place. If it is yes, then it will be C, then B, then A. Like this. So this is the selection sort. Okay. So you will have to draw this, and by drawing this, you will be able to understand how the three elements are getting sorted. So many comparisons are there. So you can learn it step by step. First do only the left step, understand it, then go to the right step. Okay. Now let us do the time complexity. Time complexity. See, for example, the time complexity, it is they in your textbook also, they have just shown you the total time complexity and all that. They have not shown you the calculation. So in this one, I will show you how the calculation is done. Okay. For the time complexity. See here. For any decision tree, for any decision tree, there will be n factorial leaves. Okay. Okay. If there are n factorial leaves, then their height is okay. In worst complexity, it is log n to the base 2. It's not a bracket, basically. It's not a bracket. Don't get confused. Like this. Okay. Now using this, we'll find the time complexity. Let us use something called as Stirling's formula. Stirling's formula. Stirling's formula is used to find the, let me write here, Stirling's approximation is a way to estimate factorials. It is a way to estimate factorials of large n values. Stirling's formula is a way to estimate the factorials of the large amount of n. See, the formula goes like this. N factorial is, okay, square root of 2 pi n into n by e to the power n. This is your Stirling's formula. Okay, why it is used? It is used for finding the value of n factorial for large values of n. Okay, before I go to the formula, there are before I go to the calculation, let us do the uh, assumptions. Okay, there are some log formulas that you are supposed to know. Okay, one is when you have log AB to the base 2, log AB to the base 2, it is log A to the base 2 plus log B to the base 2. Log AB to the base 2 is, you can separate them by addition. One more is that if there is log A to the power of B to the base 2, then it is B into log A to the base 2. These two formulas you are supposed to remember because this will be helpful in the calculation part. Okay. These are the formulas that you will use. Now let us do for our formula. Okay, so our formula is this log this one. Okay, now with respect to this, let us find. So according to this formula, it is log to the base 2. N factorial is square root of 2 pi n into n of e to n by e to the base n. This will be the formula, correct? N factorial. Now you see here, there are two terms basically. One term is this and the other term is this. Okay, let me call this as formula 1 and this is formula 2. See here, two parts are there. I'll assume this as A and this as B. Now I'll try to calculate them, okay, using that formula. So it will be log to the base 2, first part, 2 pi n, plus log to the base 2, n by e to the power n. This is what I will get. Okay. Now let me try to calculate these two separately. I'll calculate these two separately. Okay. This I'll call it as, I'll calculate this in the side. Okay. See, I'll calculate only the left part. Log square root 2 pi n to the base 2. Okay. So this will be, see, because there is square root, I'll take that square root. So it will be half into log 2. Then you'll have 2 pi n. Correct? 2 pi n. Again, here again there are two terms. See, 2 pi is 1 and n is 1. So I'll take this as A and this as B. Okay. So what I will do, I will calculate it separately. See, so it will be half into half into log of 2 pi to the base 2 plus half into log of n to the base 2. I have separated them. Okay. This is your left part. Let me do the right part. I'll do it here. So the right part is this. Okay. So let me do the right part. So right part is log n by e to the base n. Sorry, to the power n to the base 2. Now, this formula I will use, this second formula. See, log a to the power of b base 2 is b into. So, b here is n. So, n into log n by e to the base 2. Okay. So, here again you have this simplified form. So, n into n by e can be considered as log n to the base e base 2 minus log e to the base 2. Okay. So this will become n log n to the base 2 minus log, sorry, not log, n log n into log e to the base 2. So this is left side and this is right side. Now you combine both. So it will be, I'll combine both. After this step, I will combine here. So left side is half into log 2 2 pi plus half into log n to the base 2 plus n into log n to the base 2 minus n into log e to the base 2. Okay. Now, you know that there are 4 terms. Okay. These are the 4 terms. But in your time complexity, what do we do when we calculate the time complexity? If there are 2 terms, we take the term which is having the highest or more value. Correct? So here you have half. Here also you have, this first one is having half. Second one is also having half. And the fourth one is n into log e. So what we do is we consider only the one with the highest value being for this one. So ignoring the other terms, we'll only consider the one with the higher value, that is this one. So it is not E, it is 2, right? This is not E, this is 2. Hold on, here also let me erase. It is 2. Okay. So when you're telling about the complexity is theta of n log n to the base 2, or when you're considering the lower bound, that means your best time complexity, that means your time complexity will come as omega of n into log n to the base 2. So if they ask you to do the time complexity for selection sort, you can do it like this. Steps might look lengthy, but they're not complicated. Practice this once or twice, understand the formulas and substitute. That's all. Okay. So this should be your answer. Okay. That is about the selection sort. You will have to write the you'll have to write the decision tree as well as derive the time complexity. This one. Okay. Now let us look at the third decision tree. The third decision tree is for insertion sort. Insertion sort is the third one. Again, that is also very easy. Let us do that part. Selection insertions. Okay. Okay. Now let us continue with the next decision tree. This is a decision tree for insertion sort. Okay. So 3 elements A, B, and C. So A less than B initially. So initially the elements are A, B, and C. If it is yes, and if it is no. Okay, if it is no, if A is not less than B, then the order will be B, A, and C. Here the two adjacent elements are compared. Okay. Next, here, if it is yes, the order remains the same, A, B, and C. Next, if it is so, if A and B is compared, let us compare the next two elements, B and C. If it is yes and if it is no. If it is yes, then the order remains the same, that is A less than B less than C. If it is no, the order will change to A, then C, then B, because B is not less than C, so C is the smallest. Now again, I'll compare A and C, whether they are in the correct position. If it is yes, and if it is no. If it is no, the order is C, then A, then B. Correct? If it is yes, then the order remains the same. A, then C, then B. See here, if A is less than B, if it is not, then the order changes, B, A, and C. Now I'll compare A and C. A is less than C. If it is yes, no problem. If it is yes, then the order remains the same, B, then A, then C. No problem. But if it is not, then C is the smallest, so it will change its place. Now you will compare B and C again. If it is yes, order remains the same. So B, then C, then A. If it is not, the order is B, then A, then C. Sorry, 1 minute. Here, if B is not less than C, that means C is the biggest, no? So C. So here, if B is not less than C, that means C is the smallest, right? So C will come first, followed by B, then A. So this is for the insertion sort. Okay, when you do the decision tree for the insertion sort. Now you see here, while you do the time complexity, okay. See, decision tree can be used for analyzing the average complexity. Okay, this decision trees can be used for analyzing the average time complexity. See, we can compute the average number of comparisons for a particular algorithm as the average depth of the decision tree's leaves. So from the leaf to the root, how many positions are there? From there, you can calculate the average number of comparisons. See here, for this particular comparison, there were two decisions that were taken. Okay, two. For this one, there is one. For this result, it is 1, 2, and 3. So there are 3. Likewise, for this, again, there is 3. Okay. For the other end, this one, 1 and 2. For this one, 1, 2, and 3. Okay. Similarly, for this one, it is 1, 2, and 3. Okay. So you are getting the values like this. This divided by the total outcomes. Okay. So 1, 2, 3, 4, 5, 6 outcomes. See, this is the first outcome, second outcome, third, fourth, fifth, and sixth. There are 6 outcomes. So this divided by 6. So it will be 3 plus 3, 6, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. Okay, so your value is coming to 2 by 3. Okay, 2 by 3. Now we have the standard assumption that for all n factorial outcomes of the sorting, okay, the lower bound on the average comparisons, the lower bound on the average comparisons would always be C of averages log n factorial to the base 2. This will be the time complexity there. Number of, not time complexity, the number of comparisons. Okay, I hope you are understanding. Insertion sort also is very easy. The thing is, you will have to do this additional steps over here. Okay. Now let us look at the decision tree for binary search. Okay, the decision tree for binary search. Decision tree for binary search. We'll assume there are 4 elements. And if you remember, in case of binary search, the inputs are the elements in the ascending order. So I'll take 4 elements. So it is A of 0, A of 1, A of 2, and A of 3. 4 elements. Now I will find the mid element. Remember, in case of binary search, you have to find the mid element. Mid element is the index of low plus high by 2. So the low index is 0, high index is 3. So divided by 2. So it is 3 divided by 2, which is equal to 2.5. So I will take 2. Okay. I'll take 2. And because it is 2, this becomes a mid element. Okay. This becomes a mid element. Now let us try to construct the binary search tree. So remember, mid element is A of 1. 3 possibilities are there. Now you want to find whether the key is present or not. You will do the comparison. Okay. There are 3 possibilities. One is the key might be less than the mid element. It might be equal to the mid element, or it might be greater than the mid element. Okay. 3 possibilities are there. So key can be greater than the mid element A of 1. Okay. And if it is less or if it is greater than. See, if the key is equal to A of 1, if it is equal to A of 1, then A of 1 itself is the element that you're finding. Correct? If it is not, if the key is less than A of 1, okay, remember the elements are these: A of 0, A of 1, A of 2, and A of 3. So, if the element you are searching is less than A of 1, which is the element which is less than A of 1? A of 0. Okay. Similarly, if it is greater than A of 1, if it is greater than A of 1, it can be either A of 2 or A of 3. But before we go to A of 3, we'll have to check with A of 2. Okay. Now, let us see. If it is found, this is okay. But what about the other 2 conditions? So, for this, again, there are 3 possibilities. Okay. The key that you are searching might be lesser than A of 0. It might be equal to A of 0, or it might be greater than A of 0. If it is equal to A of 0, that itself is the key that you're finding. If it is not, see, it is greater than A of 0. For the right side, okay, I'm talking about this one. It is greater than A of 0, but less than A of 1. It is greater than A of 0, but less than A of 1. So it will be somewhere in between these two. Okay. What about this side? If it is less than A of 0, A of less 0 itself is a smallest element. If it is less than 0, that means key is not found, but we'll write it is less than A of 0. We'll not bother about whether the key is. It is obviously meaning that the key is not found. Now, let us look at these 3 conditions. So, lesser than, equal than, greater. If the key is equal to A of 2, then it is A of 2 itself. No problem. Okay. If it is greater than A of 2, if the key is greater than A of 2, if it is greater than A of 2, then we have A of 3. So A of 3 will come from. If it is not, this is not the final one. So yeah. So I'll just write A of 3. Okay. Sorry. Yeah. Like this. Now A of 2, A of 3. If it is less than A of 2, this part. So it is greater than A of 1, but less than A of 2. So it will come somewhere in this, in between these. Otherwise, it is A of 3. Now for A of 3, again we'll have, for the greater value, you'll have to do the three conditions. Okay, so it can be lesser than, it can be equal to, or it can be greater than. If it is equal to, then it is that element itself. If it is not, see, with respect to A of 2, so it is greater than A of 2 and lesser than A of 3. So it is anywhere between A of 2 and A of 3. And if it is greater than, that means an element is greater than A of 3. That means element is not found. So this will be greater than. So like this. This will be for the binary search tree. Okay. So you will have to divide the array into two parts and then do the three comparisons. Similarly, there is one more, when you're doing the comparisons, there is, when you're doing the comparison, number of comparison at worst case is, number of comparisons at worst case is C of binary search, worst capacity, worst comparisons is log n to the base 2 plus 1, which is equal to, 1 minute. It is this plus 1 comparison. So together it is the floor value of this. This will be for your binary search. Next you have the last one, that is the binary decision tree. Binary decision tree for binary search in a 4-element array. Binary decision tree, sort of like, instead of having three conditions, three comparisons, here you will have two comparisons. See, again we'll take with respect to 4 elements. Okay, A of 0, A of 1, A of 2 and A of 3. Again find the mid element. Mid element is 0 plus 3 divided by 2, 2.5. So I'll take test 2 itself. So A of 1, second element. Okay. So A of 1. So only two possibilities are there. Either it is greater than or lesser than. So lesser than and greater than. If it is lesser than A of 1, it will become A of 0. If it is greater than, then it becomes A of 2. Similarly for this, if it is lesser than and greater than. If it is lesser than, then it is lesser than A of 0. So if it is this part, then it is lesser than A of 1, but greater than A of 0. So it will come anywhere between A of 0 and A of 1. Like this. If it is not, It can be lesser than or greater than. If it is lesser than A of 2, that means it will come in between A of 1 and A of 1 and A of 2. If it is greater than A of 2, that means it is A of 3, correct? Now lesser than and greater than. Lesser than and greater than. If it is greater than, then it is greater than A of 3, some element greater than A of 3. If it is not, then it is greater than A of 2, but lesser than A of 3. So it will come in this range. Okay. So this is how you will do the binary search, decision tree for binary search. Okay. So only true and false is there. And their number of comparison is greater than or equal to n plus 1 to the base. This is how you will do the decision tree. So we have seen a lot of things in this particular video. So kindly try to remember all the things. So we first looked at the definition of decision tree. Then we saw the decision tree for finding the minimum of 3 numbers. Then we saw selection sort, decision tree. We also saw how to calculate the time complexity of it. Then we did the decision tree for insertion sort, followed by the decision tree for binary search and the decision tree for binary search in a 4-element array with the 2 conditions only, yes or no. Okay. So that's all for this video. Thank you so much.